Hello students, welcome to this second part of our modules on our module on differential equations. In this course we are mostly discussing different solution techniques for linear differential equations. Okay, linear differential equations are ones which satisfy the property of linearity. That is, if I have a differential operator L and if it operates on, let's say, alpha 1 y1 plus alpha 2 y2, then this should be the same as alpha 1 ly1 plus alpha 2 ly2. This is the basic principle of linearity. Okay, so whenever you have a linear differential equation, then if you have y1 as a solution to that equation and y2 as a solution to the equation, then any linear combination alpha 1 y1 plus alpha 2 y2 is also a solution. Okay, this is called the principle of superposition. That is, you can solve the problem in bits and then you can add all the solutions to get the final solution. Okay, let me illustrate this with the help of an example. Suppose I have Ly, I need to solve this problem. Okay, f1 plus f2 plus 1 up to fk. As you know from the last lecture, these functions on the right side are known functions, and we need to solve the unknown function y. That is the meaning of the solution of a differential equation. In analogy, you should recall the linear system ax is equal to b, system of linear equations. This is a known or a given vector, and this is a matrix, and this is the unknown solution vector, right? In a very similar manner, okay, you could think of this as the operator, linear operator, and y is the unknown function, and these are a bunch of known functions. Okay, so that is the analogy that you should have in mind. Now, if you have L, if you set the right side to 0, okay, this is called the homogeneous problem, and these solutions are called the homogeneous solutions. The solutions to the homogeneous problem are called the homogeneous solutions. Okay, and let us say that because the system is linear, you can get the particular solution in parts. That is, you can think of L operating on yp1 is f1, L operating of yp2 is f2, and so on. Okay, now if you add them all up, then you will get L operating on, so similarly you can go all the way up to L operating on ypk is fk. Okay, suppose you add them all up, what will you get? On the right side, because these are linear operators, you will get L operating on yp1 plus yp2 plus 1 up to ypk is equal to f1 plus f2 plus 1 up to fk. Okay, but this is what we wanted to solve. That is, initially the right side, this is called the inhomogeneous term. Okay, these known functions are variously called as inhomogeneous terms, or they can also be thought of as forcing functions. Okay, so if you could not solve the problem where you have all the forcing functions on the right side in one go, you could solve it in separately. That is, you solve with only f1 as a forcing function, the solution is yp1, f2 as the forcing function, the solution is yp2, and so on. Then you will get, if you add all them up, because the system is linear, you can add it, and therefore this superposition of individual solutions will give rise to the particular solution to the entire problem. So the total solution to L y is f1 to fk is written as, you have the homogeneous solution plus all the particular solutions. Okay, this is called the principle of superposition. This is called the principle of superposition. Okay, so this is very handy in the solution of more complex linear problems. Okay, wherein if you have the forcing as a sum of various terms, then you can break down the forcing into individual terms, find the response or the solution to each of the forcing and add them all up. Okay, this is not true only of forcing in the differential equation. You can also have forcing in the boundary condition. That is, suppose I have an equation like this: d squared t by dx squared is 0. Okay, so this is homogeneous, right? Because this is 0. So this is a homogeneous equation. But the boundary conditions can be non-homogeneous. That is, t of x is equal to 0, let's say, is a or 0. T of x is equal to L is, let's say, some t naught. Okay, so this is inhomogeneous or non-homogeneous. So the forcing happens in the boundary condition, even though the governing equation is homogeneous. Okay, so the homogeneity or inhomogeneity should be judged based on whether both the governing equations and the boundary conditions are homogeneous in the case of differential equations. Okay, this is something that you should keep in mind. So a homogeneous problem in a differential equation will correspond to both the differential equation and boundary condition being homogeneous. Okay, so now let us take a slight detour, and I want to very briefly tell you how to solve ODEs, solution of ODEs using the Laplace transform method. You know this already from earlier courses on process dynamics and control. Okay, but nonetheless, because we developed the idea of Laplace transform and we also discussed how to invert Laplace transform using the Brown-Witch contours. Okay, so right now we are looking at ODEs, and the Laplace transform method is suitable or is suited for initial value problems. We'll come to how to solve ODEs using how to solve boundary value problems of ODEs shortly. So in short, I'll call them IVPs. Okay, initial value problems. Okay, so when is the Laplace transform valid, or when is it convenient to use? This is convenient to use for ODEs with constant coefficients. That is, the coefficients, if independent variable, the coefficients, obviously the ODE should be linear. The coefficients should be independent of the independent variable. Let's say time. Okay, suppose you have an ODE. Okay, so you should not have this, should not be a function of time, should be some constant number like 5 or something like that. Okay, it should not be a function of time. Okay, so the Laplace transform method is valid, or it's convenient to solve linear ODEs with constant coefficients. The key idea is, once you transform the linear ODE, the ODE becomes transformed to an algebraic equation. ODE in time becomes algebraic in the Laplace variable S. Okay, now we solve the algebraic equation of the transformed equation. Solve the algebraic equation for, let's say, y of S. Let's say the ODE is in y of t. Then if you transform it, you will get y bar of S. Once you solve for y bar of S, invert y bar of s using the inverse Laplace transform that we discussed earlier to obtain y of t. Okay, of course I will illustrate this with an example. Okay, recall the LT pair, the Laplace transform pair. Okay, so you recall the Laplace transform pair f bar of s is 0 to infinity f of t e to the minus st dt, and you have f of t is minus infinity to infinity f bar of s e to the st ds, and you will also have 1 over 2 pi I. Okay, and sorry, this is not minus infinity to infinity, this is gamma minus I infinity to gamma plus I infinity. Okay, where gamma is chosen so that this is where gamma is chosen such that this is a decaying function, this combination is a decaying function. Okay, so if you recall the complex plane, okay, now gamma should be chosen such that it is far to the right of any poles in the Laplace transform. Okay, so this is gamma minus I infinity, gamma plus I infinity. The function f bar of s may have many simple poles, so you should place your the Brown-Witch contour over which you are integrating to the right of all the singularities in the function f bar of s. That was what we discussed long back. Okay, now the key thing that you have to first understand is that if I have f bar of s is 0 to infinity f of t e to the minus st dt. Okay, now I want to know what is the Laplace transform of f bar of s is the Laplace transform of f of t. Okay, what is the Laplace transform of df dt, okay, or f prime of t, okay, which I will call f bar prime of s. Okay, this is the Laplace transform of df dt. Okay, so what do we do? How do we do this? Okay, now you know that okay, so okay, so in order to find f bar of s, what we need is, instead of f of t, you will have df dt e to the minus st dt. Okay, that is the definition of, this is the Laplace transform of df dt. So if you want the Laplace transform of any function, you have to put that function. If you want Laplace transform of f of t, you should put f of t. If you want the Laplace transform of df dt, you should put df dt here. Now we integrate by parts. Okay, let's call this u, let's call this dv. Okay, so you'll get is uv minus integral v f of t, and then du, which becomes minus s e to the minus st dt. Okay, so the Laplace transform of df dt, which is denoted as f bar of s, is nothing but, so I have to apply the conditions here, right? This is e to the minus st f of t at t is equal to, or t tending to infinity, minus e to the minus st f of t equal to 0. Okay, now if I take this, this becomes plus s integral 0 to infinity f of t e to the minus st dt. Okay, so okay, let's now understand what each of these terms are. Now this term in the bracket is actually f of s, right? Because that is the definition of this is nothing but f bar of s, right? This is f bar of s. Okay. Now as t goes to infinity, we know that s this thing has to go to 0. Okay. So as t goes to infinity, this is e to the minus s infinity. So this goes to 0. Okay, and we know that we have chosen e to the minus t f such that e to the minus t f of t is always decaying as t goes to infinity. Only then we could define the Laplace transform. Now here you will have minus of, now t goes to 0, this becomes 1, f of t equal to 0. Okay, so let me take a new page. The Laplace transform of df dt is denoted as f bar is equal to minus, okay, f at time t equal to 0 plus s f bar of s. Now similarly you can also do in the same way using integration by parts the Laplace transform of the second derivative, okay, of t d squared t by d squared f by dt squared, and that you will find to be minus f prime at t equal to 0, okay, minus s of f t equal to 0 plus s squared f bar of s. So all the derivatives are now written as some algebraic expression, such as there is no time derivative in s, it's only s times f bar of s, s squared times f bar of s. Now what about these terms? How do you find out these terms? These are usually obtained from the initial conditions for f of t. Remember that if you want to solve an ODE, you have to supply initial conditions. If you want to solve a second order ODE, you need two initial conditions and so on. So we have to use the initial conditions to complete the problem. Okay, so let's take an example. Let's say we want the Laplace, we want to solve d squared y by dt squared minus 3 dy by dt plus 2y is equal to 2e to the minus t. Now we are given that y at t equal to 0 is 2, y prime, that is dy by dt, is 1. Okay, let's say this is the problem that we want to solve. So we have to take the Laplace transform of the entire equation first. Okay, so this will give us s squared y bar of s minus y at t equal to 0 minus y prime at t equal to 0 minus 3 times the Laplace transform of dy by dt is s y bar of s minus y at t equal to 0 plus this term will simply give me 2y bar of s, and the right side will give me the Laplace transform of e to the minus t is 1 over 1 plus s or s plus 1. Okay, right. So we know what these are. Y at t equal to 0 is 2. Okay, y prime at t is equal to 0 is 1. So this is again 2. So after substitute, because these are the initial conditions. Okay, after substituting all this, you will get, right, you will get s cubed minus 3s plus 2 sorry, it should be s squared. Okay, this is s squared. I'm pulling out coefficients of y bar of s, minus 3s plus 2 y bar of s, right? Now minus 2s, this is this, minus 1, and then you had this is simply minus 3 times minus 2, which is plus 6, is equal to 2 by s plus 1. Okay, so this is s squared minus 3s plus 2 y bar of s. Okay, and this is simply minus 2s plus 5, right? Minus 2s plus 5 is equal to 2 by s plus 1. Okay, so if I were to take this to the other side, s squared minus 3s plus 2 y bar of s is 2 by s plus 1, okay, plus 2s minus 5. Okay, so y bar of s is nothing but 2 by s plus 1 plus 2s minus 5 times s plus 1. This is, and you take this to the other side, s squared minus 3s plus 2. Okay, so you will get finally, if you simplify this, it's 2 plus 2s squared plus 2s minus 5s minus 5 by s plus 1, and if I factorize this, I will get s minus 1, s minus 2, right? If I factor this quadratic, now if I simplify this further, I'll get 2s squared, okay, this is minus 3s minus 3 upon s plus 1, s minus 1, s minus 2. Using partial fractions, you can write this as s plus 1 plus 2 by s minus 1 minus 1 by 3 s minus 2. This is y bar of s. Now it's easy for you to invert this because you have a sum of 3 terms, right? So y bar of s is 1 by 3 s plus 1 plus 2 by s minus 1 minus 1 by 3 s minus 2. Then y of t, inverse Laplace transform, using the method that we discussed long ago in complex analysis. I won't go into the details. So this is 1 by 3 e to the minus t plus 2 e to the plus t, sorry, minus 1 by 3 e to the 2t. Okay, so this is the final solution, and this satisfies the initial condition. So let's check. Y at t equal to 0 is 1 by 3 into 1 plus 2 minus 1 by 3 into 1. So y at t equal to 0 is 2, which is what we started off with, and you can similarly verify that y prime at t equal to 0 also becomes 1. So this satisfies the differential equation as well as the initial conditions. So this is how we solve initial value problems of linear differential equations with constant coefficients using Laplace transform. Okay, now I'm going to again slightly change gears, and now I'm going to discuss how we can use the method of eigenfunction expansions as a way of solving differential equations. First, let's start with ODEs, ordinary differential equations, and then we will slowly graduate to PDEs as we go along. Okay, again, this method works for linear ODEs or PDEs. Okay, PDEs will come a little bit later. Okay, and it exploits the principle of superposition. Okay. Now to begin with, let's take an example from system of linear equations in finite dimensions. Let's say you are interested in solving Ax equal to b. Now instead of solving it using Gaussian elimination or something along those lines, let's say we first solve the eigenvalue problem. Axi is lambda xi. This is the eigenvalue problem for the matrix A. Okay, so now, and let's further assume that you have n linearly independent or orthogonal, even orthogonal would be better, eigenvectors. Okay, okay, so now if you have n linearly independent or orthogonal eigenvectors, I can expand the unknown solution vector in terms of the eigenfunctions. Let's take the notation, let's change the notation slightly. Let's take the eigenfunctions as EIs, okay, where these are the coefficients of expansion. Okay, these are the eigenvectors, okay, of this problem, of the eigenvalue problem for A. Okay, so this is I going from 1 to n. So I substitute this A, this x expansion here, A times summation Ci Ei is B. Now because the operator is linear, this is a linear operator, this is a matrix, matrices are linear operators, remember. So this is A summation I is equal to 1 to n, right? Ci, these are constants, so I can write this as AEI is equal to B, but AEI is nothing but lambda I EI, that's the eigenvalue problem. So I can write this as summation I is equal to 1 to n Ci lambda I EI is equal to B, right? Now I want to find the coefficients Ci, but I know that EIs are orthonormal. So I take the inner product with respect to Ej, so I'll get I is equal to 1 to n Ci lambda I Ej Ei is equal to Ej inner product B. This is a known vector, right? So Ej Ei, so this is a comma, I'm sorry. Okay, so this is delta Ij. So I'll get, if this delta Ij with this summation will change okay, with this summation will change the Ci to Cj, and the lambda I to lambda j is Ej B, or Cj is Ej inner product B divided by lambda j. Okay, so this is the solution to the problem, because this is the solution to the problem Ax is equal to B, because once I know Cj's, I know what x's are, because x's are nothing but j is equal to 1 to n Cj Ej, and I know the eigenvectors already. I have solved the eigenvalue problem. Now you might say, what is the advantage of this? The advantage of this is, once you have solved this problem in this manner, you can plug in any b and you have a solution. Okay, if there is a solution, of course that aspect is there, that there must be a solution. Okay, if there is a solution to this linear system, then it can be readily obtained like this. Now the same method can be generalized for any operator, not just matrix operator or system of linear equations. Imagine that you need to solve a differential equation of the following form: L y of x is equal to f of x with suitable boundary conditions. Okay, now so this is known. So first solve the eigenvalue problem for L. L is a differential operator. To be specific, it's a linear differential operator. So first solve the eigenvalue problem. So L, let's say phi I of x is equal to lambda I phi I of x. These are the eigenfunctions. Okay, and let's further assume that L is a self-adjoint operator, meaning phi I phi j is delta ij. It generates orthogonal eigenfunction, and let's say L has distinct eigenvalues and so on. Now y of x can then be expanded. This is called eigenfunction expansion. You expand y in terms of the eigenfunctions of the operator L. Okay, and these are the coefficients like before to be found. So instead of the unknown function y of x, you are now saying that I'll find only the unknown coefficients ci. Now you substitute this in the original equation, so you'll get L y of x is equal to L summation I is equal to 1 to n ci phi I of x is f of x. Okay, but L operating on this summation is ci L phi I of x is equal to f of x, but L phi I is nothing but lambda I phi I of x. Okay, so I can write this as summation I is equal to 1 to n ci lambda I phi I of x is equal to f of x. Now to find ci's, I take inner product, use orthonormality. Phi I phi j is delta ij. Okay, so once I do that, I'll get I equals 1 to n. I take inner product with respect to phi j is equal to phi j f of x. Now this quantity is delta ij. Okay, so you get, therefore this delta ij will kill the summation and change ci to cj. Cj lambda j is phi j f of x. Okay, or cj is phi j f of x by lambda j. This is the solution, because once you know what cj's are, then you can find the solution y of x is nothing but summation cj phi j of x. Okay, so if you look at this procedure, what I just did with the earlier procedure for a system of linear equations, there is nothing that has changed. Okay, the only detail that is different is the solution of the eigenvalue problem. This is a differential equation, whereas previously you had a matrix eigenvalue problem. But other than that, every step is identical. Okay, so this is how one solves the let's say a simple linear inhomogeneous differential equation using the method of eigenfunction expansions. Okay, let's take an example, a very simple example. So let's say L, the differential operator Ly is nothing but minus d squared by dt squared y. That is, L is minus d squared. Now first solve the eigenvalue problem. What is it? L phi n is lambda n phi n, that is d squared phi n by dt squared is lambda n phi n, or d squared phi n by dt squared plus lambda n phi n is 0. Okay, instead of lambda n, let's call lambda n as omega n squared, because the algebra will become simple. So the eigenvalue problem is, okay, we are free to change the form of the eigenvalue, whether it is lambda or omega squared, it's up to us. Okay, so the solutions are the eigenfunctions phi n of t, okay, nothing but a cos omega n t plus b, sine omega n t. Okay, now let's assume that we have periodic boundary conditions. Okay, we have not specified the boundary conditions yet. Let's say the boundary conditions are periodic, that phi n at t equal to 0 is phi n at let's say the boundary is such that it is at t, capital T. Okay, that is the domain 0 to t. Okay, now therefore if I do this, phi n at t equal to 0 is a, phi n s t, small t is equal to capital T is a cos omega n t plus b sine omega n t. This means that if this has to be equal, cos omega n t is equal to 1 and sine omega n t equal to 0. That means that okay, omega n t has to be 2 pi n, where n is an integer, okay, 0, 1, 2 and so on. So omega n is nothing but 2 pi n upon t. Okay, right? So phi n of t is a cos 2 pi n upon tt plus b sine, okay, where n goes from 0, 1, 2 and so on. Okay, this is the eigenvalue problem. Now once you have solved the eigenvalue problem and you know that these eigenfunctions are orthogonal, and therefore you can express the solution of any other problem, d squared y by dt squared is some function of t. If this is the problem that you are interested in solving, then you can solve it in the same way that we just illustrated in the general discussion we just had. Okay, now one important thing is that sometimes you may have the eigenvalue problem will look like this. So L phi I of x is lambda I, rho of x phi I of x. That is, it's not that ax is equal to lambda x. You can have ax is lambda bx. Okay, you might also have something like this in the case of linear system of equations, matrix eigenvalue problem. You may have something like this. The analogous situation is here. Okay, this is also possible, and these are also eigenvalue problems. Okay, all right. Now one important thing about the eigenvalue problem is that if this is a self-adjoint operator, that is L is equal to L dagger, then the eigenvalue problem has real eigenvalues and eigenfunctions corresponding to distinct eigenvalues are orthogonal. This is very similar to what you saw in matrices. The same thing holds in the case of differential operators as well. Okay, there is nothing that changes. Okay, so this is something that is very, very important to remember, that and this is what helps us in solving differential equations using the method of eigenfunction expansions, the fact that you can generate orthogonal eigenfunctions. Now the definition of an adjoint operator remains similar. Adjoint of L, the adjoint of L is denoted as L dagger. Okay, so it's defined in the same way. F LG is L dagger F G. Okay, now the key thing about differential operators is that when you write it like this, you will also have some boundary terms. I'll illustrate this with the help of an example. Okay, so the meaning is A to B, some domain f star of x operating on L g of x is equal to A to B. This is L dagger f of x whole star, the complex conjugate, times g of x dx plus boundary terms. Okay, so boundary terms must be evaluated using the boundary conditions at x is equal to a and x is equal to b. Okay, so you can find the adjoint operator of any differential operator by doing integration by parts. I'll illustrate this with the help of an example. The operator is self-adjoint if L is equal to L dagger or Hermitian and the boundary terms vanish. The key thing is the boundary terms should vanish. Okay, now some textbooks call when L is equal to L dagger the operator to be self-adjoint, and if this is satisfied plus when the boundary terms vanish, they call the operator to be Hermitian, but I will not make that distinction. So I will take self-adjoint and Hermitian to mean the same thing, in the sense that you have the differential operator L is the same as its adjoint and the boundary terms will vanish. Okay, so let's take the simple example. Let's take L is equal to t squared by dt squared. The question is L self-adjoint? That's the question that we are asking. Okay, right? So right now let's consider the inner product f L g. Okay, this is, let's say, t naught to t naught plus t f star d squared g by dt squared dt. I integrate by parts to using integral u dv. This is uv. I'll consider this as u and this as dv. So this is uv minus integral v du. Okay, so v is now there is a second integration by parts, so that is equal to f star dg by dt t0 plus t minus, I'll consider this as u and this as dv. This is uv and then minus of minus plus integral v du okay dt, right? So now if you had this equal to this, the operator has indeed become self-adjoint, because FLG is LFG plus boundary terms. Okay, this part is the same. Okay, because if you notice this operator is the same as this operator. Okay, let me draw it slightly better. Okay, now but what about the boundary terms? That is something that we have to, these are the boundary terms. Okay, so if the operator is self-adjoint, then we need f star dg by dt t naught plus t. The boundary terms must vanish. For the boundary terms, in order for the boundary terms to vanish, we require this is equal to df star by dt g. Okay, so then you will find that L is self-adjoint or Hermitian. Okay. Now you have to choose boundary conditions that are periodic or Dirichlet. For example, you can say f of t equal to 0, sorry, t is equal to t0 is f of t0 plus t is 0, and similarly g, okay, of t equal to t0 is g of t0 plus t equal to 0. These are called Dirichlet conditions, as we have seen earlier. Or you can say that df dt has to be 0, okay, at both t0 and t0 plus t. Or you can say that the function is periodic. In all these cases, these boundary terms will vanish, and therefore L is self-adjoint, and the eigenfunctions it generates are therefore orthonormal, okay, orthogonal, and of course you can normalize them trivially. Okay, so this is one of the most important ideas that you can, in order to show that whether L is a given operator is self-adjoint or not, you have to undergo this process of integration by parts and make sure that the boundary terms also vanish. Okay, then L is self-adjoint. If L is self-adjoint, then it is guaranteed to have real eigenvalues and eigenvalues corresponding to distinct eigenfunctions corresponding to distinct eigenvalues are orthogonal. Okay, so this is something that that we can show in the context of even differential operators, but I will not, in the interest of time, I will not show it explicitly, but it's the same idea as in the case of matrices, right? So you will always have orthogonal eigenfunctions if the operator is Hermitian and the eigenvalues are real. Okay, and so there is one last thing about eigenfunctions: completeness of eigenfunctions. If the eigenfunctions are complete, then any function can be expanded in terms of the eigenfunctions. Okay, these are, let's say, eigenfunctions of L, the Hermitian or self-adjoint operator. Okay, now how do you find Cn? Cn is found as you take the orthogonal, or sorry, inner product of phi n with f, then you will get Cn. That is nothing but some domain A to B, phi n star of x, f of x, dx. Okay, so therefore f of x is nothing but summation n phi n of x times, instead of Cn I'm going to substitute this integral, A to B phi n star of x, f of x dx. Okay, therefore I rewrite this slightly. F of x is nothing but A to B, right? I'm going to write this f of x outside, take the integral and interchange it with the sum. So let's just keep it like this. I'm sorry about this. Let's keep it like this, A to B. This f of x I'm going to write here. Okay, and then I'll take the sum, n is equal to 0 to infinity, phi n cap of x, phi n star of x, okay, and dx. Okay, now look at this combination. This is f of x, this is integral f of x dx. Okay, there is one small change. Because this is f of x, I have to use a dummy variable instead of x itself. So instead of x I will use z, phi n of z, okay, f of z dz. Because f of x is already here, I cannot use the same variable, it leads to confusion. Z d dz z. Okay, now you look at this combination. Now f of x is integral a to b f of x times something times dz. What is that something? That something is here. Now what should this be in order for this to have f of x? I'm again sorry about this. This should also be f of z. Okay, I hope I have it right here. Yes, right. So this is f of z. Now if you recall the property of Dirac delta function, you will know that this has to have delta of x minus z. Then if that is the case, okay, then you will have f of z delta of x minus z dz integrated over the domain gives f of x back. So that means that delta of x minus z is given by the summation phi n of z phi n star of z. Okay, right. So this is called completeness or closure. In the context of matrices, we call this the resolution of identity. If you remember, you wrote the identity as sum of the eigenfunctions zi and zi dagger zi or something like that, if you remember, right? Or zi dagger. I'm sorry about this. Okay, I is equal to 1 to n. In the same way, instead of identity, you have this delta function, the Dirac delta function. This guarantees if your eigenfunctions sum to delta of x minus z, then your eigenfunctions are said to be complete. That is, we have a finite set of eigenfunctions, and if you have a set of eigenfunctions for a given eigenvalue problem, differential eigenvalue problem, if you sum them all up in this fashion, and okay, there is one small change that we should have here. Just give me 1 minute. One of it is x, because if you remember, phi n is x. Okay, this is x, only this part is z. Okay, so this is x, so this is x, because you have x and z, and obviously you need to have x and z on this side as well. Okay, so this is called completeness, okay? Condition for completeness of eigenfunctions. How do you know that the set of eigenfunctions are complete, in the sense that you are guaranteed that any function can be expanded in terms of the eigenfunctions for the given domain, and okay, for the given problem. Okay, now there is a class of differential operators or differential equations called the Sturm-Liouville equations, second order eigenvalue problems, which are already shown to be self-adjoint, and therefore they are guaranteed to have orthogonal eigenfunctions. What is that Sturm-Liouville equation? The Sturm-Liouville equation, the operator is minus d dx of p of x d dx plus q of x. Now this, if you take this equation, Ly is lambda y, okay, and lambda rho y. In general, I told you that the generalized eigenvalue problem is lambda rho y. Then you can show that L is self-adjoint, okay, and the boundary terms, if the boundary terms are also, L is equal to L dagger plus boundary terms. Sorry, let's be more careful about this. in order for the operator to be self-adjoint, we had U times LV is LU V plus boundary terms. Right? If I take this operator where P of x and Q of x are functions and solve this eigenvalue problem, right, then if this operator will satisfy this always, and you can choose the boundary terms to be identically 0, okay, then it is this operator is guaranteed to have orthogonal eigenfunctions. Now this is a very general operator. If I put P of x is 1 and Q of x is 0 and rho is 1, you have the usual eigenvalue problem for sines and cosines. But the beauty of this operator is that more complicated differential equations are already shown to be self-adjoint, because the Bessel differential equation, the Chebyshev differential equation, Hermite differential equation, and of course this sine and cosine, they all come under this template of eigenvalue problems, and they are all these differential operators are all these differential equations corresponding to Bessel differential equation, Chebyshev, Hermite, or the usual simple harmonic oscillator equation. They are all in this template, and they are all self-adjoint provided you choose the boundary terms to be 0, and therefore you can in all these cases you get orthogonal eigenfunctions. If you solve the simple harmonic oscillator problem, that is d squared y by dt squared plus lambda squared or omega squared y, you get sines and cosines. If you solve the Bessel differential equation, you get the Bessel functions as orthogonal eigenfunctions. If you solve the Chebyshev differential equation, you get the Chebyshev functions or Chebyshev polynomials, Hermite polynomials, and so on. So there are many general class of differential equations which are in this format of Sturm-Liouville equation, and this equation, once you are able to reframe your differential equation in the Sturm-Liouville format, then people have already shown, although I will not take the time to show it here due to lack of in the interest of time, okay, it is already shown to be self-adjoint provided the boundary terms are chosen to vanish. Therefore you are guaranteed to get orthogonal eigenfunctions. So what I will do is I'll stop here. In the next module we'll start discussing how to use this method of eigenfunction expansions to solve ODEs and PDEs and take it further. Thank you.